So good afternoon, everybody. I hope you remember what we did in last class. Till now, we were talking about uh, different crystal structures, how a good 3D periodicity is, how the good crystalline structures are. We talked about some simple structures. We also talked about some complex structures. And then we saw how structure gives rise to a particular property. Okay. So today, in today's class, we will start another topic, which is a very, very interesting topic when it comes to materials, is defects. So let's start. नहीं, दूसरी. Yeah. Okay. So defects, okay, defects, the word as such in English has a very negative connotation to it, It basically means something is not perfect, something is not right. But it is good to have defects also. Like, all even the human beings, none of us is without a flaw. All of us have flaws, and it is our flaws which makes us what we are, which makes me what I am, which makes you what you are. So flaws are also important and interesting, and it is flaws that, other than the good things, that actually make up a person, right? So after that general thing, uh, what are basically defects? When we say defects in solid, okay, a very first picture that would come to your mind is anything at all that is breaking the three-dimensional regular arrangement in a crystalline solid, and I would call that as defect. Why? Because it is breaking up the 3D periodicity, right? So when we define it, we say that imperfections in the regular geometrical arrangement of atoms in the crystalline solid are called defect. But are they important? What do they really affect? Of course, defect in solids is a complete branch of science and a very interesting branch of material science. Why? Because by controlling defects, by introducing defects, by reducing defects, basically by playing with defects, you can alter the mechanical properties, you can alter the electrical properties, you can alter optical behavior, you can alter chemical reactivity. The you can introduce the other day somebody was asking how can we create sites for sorption or ion exchange? Defects do that. So obviously, anything you have a 3D periodic arrangement, it has its own nature, and suddenly you rupture it at some point, and that is a very small part of that 3D fabric, but it alters it so much that you're able to kind of introduce or modify the properties, and that is what make defects interesting. Okay, so of course, perfection is boring, and who wants perfection? If everybody's perfect, we'll not have anybody to talk about. So, all of us have imperfection, as I just mentioned a minute back. That is what makes us unique and beautiful in our own individual ways. And that is how real solids are. They are like people, they are imperfect. And a very famous scientist, John Corrick, mentioned that it is actually the defects that makes the solid interesting and impart them their properties. Okay, so what are the three things that control the property of the material? If you close your eyes and I just ask you to name three things that would affect the property of a material, even if you are a layman, layman, I mean, of course, with the knowledge of science, you would say that bonding, we know whether it is ionic bond, metallic bond, covalent bond, that affects the property. It's crystalline structure. We spent the entire last lecture on this. Okay. So these two are the inherent thing. Okay. By varying that, also we can control the property. Now you have got a material and then now you process it. Even that inherent thing will also introduce some defects which cannot be avoided, which we will talk about in the next few slides. But suppose you prepared the material, it has got some sort of bonding, some sort of structure, By macro processing it, making pellets, making shapes out of it, there also you introduce defects. So the factors that controls the properties of the material are bonding, its structure, and the defects. Okay. So how and why do actually defects occur? Of course, you beat somebody and he will get hurt. Similarly, you can deform a crystal, defects would be introduced. Okay, suppose you're growing a single crystal, you rapidly cool it from the high temperature. It will introduce some defect in it because if you grow the crystal slowly, the probability of you getting a perfect crystal are more as compared to when you rapidly cool it from high temperature. It's kind of a shock. You give a shock to it, defects would be introduced. Then external processes, for example, exposure to high energy radiation. We talked about the relation between radiation stability and crystal structure in last class. What does radiation do? Radiation deposits energy. What does energy do? It will be utilized in some way, knocking off the atom, making some bond, breaking some bond. That creates defect. Any disturbance during the synthesis process create defect. But most important, all these defects, whatever I just talked about, you can kind of, control them. But there are certain defects which arise due to thermodynamic reasons, and you go to the best lab in the world, you adopt the best synthesis strategies, the defects due to thermodynamics cannot be controlled. Okay? What are the simplest form of defect that will occur in a 3D lattice? One is vacancy. Okay. And what is a vacancy? It is an unoccupied atom site. An atom has been knocked off from its regular lattice site, and what you get is a vacancy. All right. Or an interstitial. In this 3D arrangement of atom, some extra atom has come from somewhere and occupied a position, an interstices. So that interstitial is another simplest form of defect. Okay, and just going a little forward, even though we will talk about it a little later, if you try to imagine around this vacancy that is shown here, if we have an empty space, the nearest neighbor atom that are trying to that are surrounding it, they will try to kind of there's an empty space, they kind of jostle in a little. Okay, so you have some kind of a deformation that occurs because now these atoms will be slightly moving towards inside this vacant void. Okay. Now, similarly for interstitial, howsoever small the atom is, once you have placed it in the interstices, it will try to push the neighbors, and that also creates a kind of stress. This is how even a simple vacancy and interstitial can cause deformation in the local structure of the material where they appear. Now, how can I classify the defect? I mean, defect is a defect. How does it matter? You ask me whether I classify it or not. We classify the defect because as it makes us easier to once we observe a defect or once we observe a property which we attribute to a particular defect, particular reason, it helps us to kind of channelize it. Okay, this is due to this, and because it looks like this kind of thing, so it will belong to a particular class. So that is why defects are classified, and there are various ways you classify the defect. First is on the basis of thermodynamic factors, which you cannot control. Dimensionality. We will talk about it, but dimensionality means whether it is located to only a particular lattice site, or it has 2 dimension, or it has 3 dimension, and so on. Then stoichiometry changes. Stoichiometry changes means suppose you have a formula AbO3. Okay, I try to put something in that changes the number of oxygen ions in it. Of course, that will create a defect. So stoichiometry changes can lead to defect, and that is majorly done by formation of solid solution. And we'll have an entire some 20 minutes lecture on what solid solutions are. And intrinsic and extrinsic. Again, intrinsic means the factors that you cannot control, the defect would happen, and thermodynamic factor, defect due to thermodynamic factors, they lie in the intrinsic. Or extrinsic, that is deliberately you have done something to introduce a particular defect. All right. Now let's talk of thermodynamic factor. Why should thermodynamic introduce the defect? Okay, so maybe you would have read about it, but it is good to kind of revise the things. Thermodynamic factors. Let us say I have a perfect crystal, a perfectly organized three-dimension crystal, even though that is not possible in reality. But let us imagine. Now I try to remove just one atom from it. Now to remove that one atom, what will I have to do? I have to break the bonds holding this atom with the neighboring atoms. Okay, and breaking of bond requires energy. All of us know. So delta H is positive. But the fact that that particular atom could have been if I talk in very real terms, that has created deformation. That is, it has increased the entropy. Now, the fact that this particular atom that I have removed from my n by n lattice could have been any of the n atoms. Okay, so that introduces a kind of uncertainty or entropy. So once I remove this, it increases the entropy. Now delta H is positive and delta S is negative. And here delta S is much more negative as compared to delta H. So its formation is favored. Now let this particular defect be in the lattice. I remove another one. Alright. Again, energy would be required to break the bonds, and removal of this would create entropy. It was a very ordered structure, and I simply went and disturbed it. So the entropy is delta S, not the entropy. Change in entropy is very large. But now let me go to a stage by removing one by one. Let us say out of that n by n lattice, I have removed 10 to 15% of balls already, atoms already. Okay. Now, if I remove after that 10 to 15%, I remove another ball, delta H will be same. It will be positive, because for every atom, the number of nearest neighbor atoms are same, number are same, उतने ही bond मुझे तोड़ने हैं, उतनी ही energy लगेगी. But now, when I have already removed 10 to 15% of atoms, now removing an extra atom, change in entropy, which I call as delta S, is not much. Already the system is pretty disturbed. Removing another ball or another atom is not going to affect it as much as it did in the initial stages. So now delta S is becoming slightly, it is saturating, and then it kind of becomes positive. Okay. But there would be some particular defect concentration where your delta H would have been equal to delta S, or let us say T delta S. So this is the reason, because of increase in entropy of the system, that leads to decrease in free energy. This is the reason that is behind the fact that whatever you do, some amount of defects you cannot avoid. And the kind of defects created due to these factors are called thermodynamically generated defect. So basically, creation of defects decreases the free energy of the system. It imparts more stability to it. Okay. Now, we'll try to see, but what happens is, when you increase the temperature, suppose this particular free energy graph was at temperature T1. Okay. Now I increase the temperature of the system. Okay, the entropy increases. Now, if entropy is, that is delta S is increased, now its negative value has also increased. So delta H minus T delta S will become 0 at some higher defect concentration. This is the x-axis is the defect concentration, and y-axis is the energy axis, H, G, S, whatever you talk about. So basically, now the equilibrium defect concentration for which your H will be equal to T delta S is shifted to the higher value. So what does temperature do? Increase in temperature increases the number of defects. Or in other words, equilibrium defect concentration increases with increase in temperature. All right. Now, what kind of defect would be created? Whether it would be a vacancy, whether it would be an interstitial, that would be decided by the defect that is easiest to form, which means which has smallest delta H. Okay, that defect for which the free energy minimum corresponds to highest possible defect concentration, that is highest delta S in simpler terms. So whether your vacancy would be formed, whether your interstitial would be formed, or whether they would cluster together, that will depend upon the defect that has got smallest delta H, जिसके bond तोड़ने में हमको सबसे कम energy लगेगी, or for which the free energy minima occurs at highest defect concentration. Okay, so and again I would because I'm teaching you all this, let me repeat. When I say a material is more prone to getting vacancies rather than interstitial, then we should also remember that we are talking about the majority defect vacancies होंगे, but interstitial बिल्कुल नहीं होंगे, ऐसा नहीं बोलते हैं. Because all sorts of cocktail of defects occur in the material, just that which one is thermodynamically more feasible is forms the majority of it. All right, I hope this is clear. Okay, so how to calculate the number of defect? Again, since this video would be on YouTube, and anyway this derivation is given in, I think it is not given in ARS, but in this form, but it would, you can find it at many places and here also. But I'll just go through it. Okay, the kind of entropy that is created in the material by removing whatever we just talked about in 2 minutes back or so, that is called configurational entropy. Okay, this. And this is given by K log natural WB. Now, what is your WB? WB is the number of states that are possible. For example, when I said that you had a completely ordered n by n arrangement of atoms, and I just want to remove one atom, that means how many ways I can remove that particular one atom. What are the different possible configurations? That is what your WB represents. Okay. So that is given by K log natural W. Okay. As I said, W is the number of ways of distributing defects over n possible sites. So I'm assuming that I have n possible sites, and the small ns is the number of defects that I'm able to, that I want to organize over these n possible sites. Okay. So W is, if I go by the probability theory, whatever we did in a class 11th or so, that says the probability of this would be n factorial upon n minus n factorial, n factorial. N is nothing but your ns. Okay. Now, if I'm creating a Schottky defect, we'll talk about that, but Schottky defect is a pair of defect, a cation defect and an anion defect. So, and these will be equal in number. So, number of ways I can create cation vacancies is this. So, similarly, the number of ways I can create the anion vacancies also would be same. So, WC is equal to WA would be this. Okay. So, total number of ways, because when I take out one cation, I have to take one anion also to maintain the electroneutrality. So, the probability will be multiplication of WC WA. So total W is WC into WA. Okay. So now the change in entropy is K log natural W. I can say K log natural WC into WA, which is, I make a square of it. Then because it is log natural, I can take 2 here. So 2K log natural, this expression. Okay. Now I use something which I call as Stirling approximation, which states that log natural of n factorial can be given by n log natural n minus n. I'm repeating each step because after the class, before putting your PCs down or shutting off, just go through this particular derivation once. All right. So once you apply this Stirling approximation to this expression, first you can expand this expression as this is log natural A by B. So you can do it log natural A minus log natural B. And then when you reach this particular stage, then you apply this formula. Okay. It will give you this. Now, this is delta S. So delta G is what is delta G? Delta G is your delta H minus T delta S. All right, and this is what has been done because there are n number of defects. So multiplying, if this is the delta H for creating one defect, then multiplying it by total number of defects. So n is delta HS, and then upper wale delta S mein I have multiplied it by T. I get 2 KT and this expression. Okay. Now our very favorite thing when we do thermodynamics. At equilibrium, my change in free energy is 0. And what is the differentiating factor here? Because I want to calculate this, the number of defects at the minima. So I differentiate my free energy with respect to number of defects, and this is what I get. Okay. And then you do all the mathematical jugglery in these two steps and you will somehow reach this step. It is very easy. That is why I don't want to do it. Okay. Now the only approximation that you have to apply is the number of the sites available to you in your crystal, n by n crystal, are much larger than the defects ns that are created on it. Because it is obvious if the defects are more, then you don't have a crystal. You don't have a 3D periodicity, and what you will left with is either the glassy or the amorphous form. All right. So once you apply this particular approximation, you replace n minus ns by n because ns is infinitesimally small as compared to your n. You get this expression. Okay. This is your number of defect. So if I ask you that I give you this much gram of NaCl, and this is the amount of energy that is required to create one defect, then tell me the ratio of defects that would be in the material at 500 vis-a-vis at the material at 300 K. You have to keep two temperatures here and calculate the ratio. So this is for one defect, okay, or ns number of defects. Converting it to the molar quantity, you will replace this by energy per mole, and you will replace your Boltzmann constant by gas constant. Okay. Now one very interesting thing. In this expression, we did W is equal to WC into WA. Why? Because I was creating a pair of defects. But suppose I'm talking of only one vacancy or one interstitial. Suppose you have a metal, gold or iron. वहाँ पे तो cation और anion नहीं है मेरे पास, सिर्फ atoms है. So the only thing we will have is W. I will not have a WC or WA. In that case, this square will go away, right? I will not have this T, 2. And as a result, in the final formula, for a vacancy or the interstitial, you will not have this 2. It will be minus delta Hs upon RT. Okay. I hope this is clear. Okay. So as I just mentioned a minute before, the defects are there, but the concentrations are very small. All right. So this is what is mentioned here. Most simple ionic solids have got low defect concentration. But अगर आप उसकी energetics change करते हो, आप temperature बढ़ाते हो, because that particular factor occurs in exponential, then you can vastly, by small changes itself, you can vastly change the defect concentration. All right. Now, thermodynamically generated defects कौन से होते हैं? Okay. Of course, this is a general term that we have been discussing in last 20 minutes. Every solid has a tendency to acquire point defect because they introduce disorder, they introduce entropy, they lower the free energy, they make your material much more stable. So what are the thermodynamically generated defects? Vacancies, interstitial, Schottky defect and Frenkel defect. What is the Schottky defect? This I will not say because this you have been reading for you also won't remember for how long. It is a pair of missing cation and anion vacancy on the crystal lattice. And Frenkel defect, it is a pair of vacancy and an interstitial. Basically, an interstitial has moved from its lattice side, occupies some position nearby. So a pair of vacancy and interstitial is called the Frenkel defect. All right. Okay. This particular slide says whatever I just mentioned on a minute back. So what happens is you have a positive and a negative ion missing from their usual lattice sites, but because a positive and a negative ion are missing, your overall stoichiometry is unaffected. That is, if you have NaCl, it would be Na1 minus X and Cl1 minus X. But the stoichiometry is Na is to Cl is still 1 is to 1. All right. Frankel defect where an atom or ion migrates from its site. This silver has migrated from its particular site to a interstitial, and now we have this situation, and this is a Frankel defect. Again, overall stoichiometry is unaffected. You have equal number of vacancies and interstitial. Okay, so this particular cartoon shows the same thing. This is your Frankel defect, and this is your pair of Schottky defect. Okay, now because in Frankel defect, Schottky defect में तो you are removing one cation and one anion. Frankel defect में जो आपका Frankel defect है, that particular atom can move either from the anionic sublattice or from the cationic sublattice. Okay, कहीं से भी जा सकता है, but the probability of getting cation Frankels are much more prevalent. Why? Because we talked about this particular thing in the close packing class also. The size of the interstices is smaller than the close packed ion. Okay. Now cations are smaller, so probability of them getting knocked off from their site and occupying the interstices, because interstices would be smaller, is more as compared to anion getting knocked off. Having said that, the very important fluoride class of material, CaF2, SrF2, ZrO2, UO2, I may add CuO2, I may add PuO2. यहाँ पे we have anion Frankel. Why? Because here the cation itself is also very, very large. So the interstices are sufficient to accommodate the anion. In fact, cerium oxide is an oxide ion conductor. Oxygen ion actually hops from side to interstices to side to interstices. Okay. We'll just discuss a very simple example. As I said, what kind of defect would be formed will actually be decided by किसका energetics favorable है, किसके लिए delta H छोटा है, किसके लिए entropy change ज़्यादा है. Okay, so we will take just one example here. NaCl, okay, NaCl and AgCl. Both of them crystallize in rock salt structure. So one thing is sorted out. They have similar structure. Okay. But your NaCl shows predominantly Schottky defect. But your AgCl shows predominantly Frankel defect. Now there are many reasons and people do theory to support it. In a very simple term, if we can understand it, it is in this way. Okay. Now ये जो cube है, what is this particular cube? You go back to your rock salt structure, and I would hate to repeat it, but I would still repeat it because I know many of you might not be in this particular frame of mind, but still, rock salt structure में at corners you have, if at corners you have cation, then at body center also you will have cation, and I'm sorry, corners and face centers would be cations, and body center and edge centers would be anions. Okay, so if I assume now in that bada cube, you try to imagine 1/8 of the cube. Suppose this is my Ag at the corner. Okay, this particular chlorine would be at the edge center. This particular chlorine would be on the other edge center. This is my Ag at the face center of the bada cube. Okay, and this particular chlorine is third axis ka edge center. This Ag is other face ka face center, and this Ag is other face ka face center, and this chlorine is actually body center chlorine. So here also you get a Q. Now where do I have interstices? This is the interstices. This is nothing but the tetrahedral interstices in your FCC unit cell. Now if this AG for creating a Frenkel defect has to move into this interstices, okay? Now what will happen is, or let's say an AG from nearby has come into this interstices and formed a Frenkel defect. Now the AG in the center, which is occupying the interstices for forming the Frenkel defect, it is surrounded by 1, 2, 3, 4 AGs and 4 chloride. Chloride से उसको problem नहीं है because chloride is negative, AG is positive. It will have electrostatic attraction to stabilize it. In case of AG, it is a highly polarizable cation. So it is not highly electropositive also. So it will not be very uncomfortable in presence of 4 like charged silver ions. But now you imagine कि यहाँ Ag की केस में अगर मेरे पास सोडियम होता था तो क्या होता था? Sodium is highly electropositive. You try to put one sodium here. If it was to create a Frenkel defect, what will happen is this sodium will be it will undergo very strong repulsion by 4 Na plus lying at this position, and it would not have been stable. That means energetically, in case of AgCl, because defect has to be created, but still Frenkel is okay. But for NaCl, if I was about to go and create a Frenkel defect, that would be energetically not favorable for it. It would have been very uncomfortable. Okay, so that is the reason NaCl shows predominantly Schottky defect and not the Frenkel defect. All right. Then other point defects. Till now we studied what are the different point defects, but thermodynamically generated are vacancies, interstitial, Schottky defect, Frenkel defect. Now there are other point defects which are of course not the thermodynamically generated defect, and color centers are one particular class of such point defect. So what is the most common color center that we've read about is F center. That F center ka full form is Farben center. Okay, and it is a German word, right? So F center में क्या होता है basically? Let's say I take my sodium. F center is nothing but an electron occupying a anion vacancy. Is an F center. And how is it created? Suppose I take sodium chloride and I heat it in sodium vapor. Sodium vapor, what will we do? They will get absorbed on the sodium chloride because I'm heating it on a bed of sodium chloride. This absorbed sodium vapor will ionize into Na plus and electrons. Okay, now this Na plus will take a chloride ion from the lattice, form an NaCl, and it will extend over the NaCl as a part of the lattice. And the electron that was released, it will migrate into the lattice and occupy the vacancy that was left by chloride ion. So this particular electron occupying the anion vacancy, इसके जो energy levels होते हैं, NaCl का energy band, NaCl is white in color because its energy band is more than what is the visible range of light. That is why we do not see any color, right? But when it electron occupies this site, it creates some other energy level in the band of NaCl. Those energy level are the gap of those energy levels are lesser than the band gap of NaCl. And ये जो difference है, this lies in the visible region. That is the reason it can absorb and emit in the visible region. And once you heat your sodium chloride in Na vapor, it gets like color, greenish yellow color. Now one interesting thing. Till now what we did talk about, that Schottky defect and Frenkel defect, they do not affect the stoichiometry. लेकिन यहाँ पे क्या हो रहा है? Suppose initially I had NaCl. Now what I have is, after all this process, Na1 plus X Cl. So now my material has become non-stoichiometric. So color center, what they also do is that they create the non-stoichiometry in the material. Okay, and the color, of course, मेरे मटेरियल पे कौन सा कलर आएगा, व्हाट वुड इट डिपेंड अपॉन? आई एम टॉकिंग अबाउट ये जो इलेक्ट्रॉन है इन anion vacancy, it acts like a particle in the box. Okay, we read about it that in the basic quantum chemistry. Particle in the box has got energy level, and in this particular situation, those energy gaps they lie in the visible region. But particle in the box, ये जो box के dimension है, ये किस पे depend करेंगे? Energy level किस पे depend करेंगे? Box के dimension पे. Box के dimension किस पे depend करेंगे? The lattice parameter of the crystal lattice that I'm talking about, which means what color would my color center give will depend not on the vapor that I'm heating in, but on the material that is being heated. That means ये NaCl को if I had exposed it to potassium vapor or rubidium vapor or cesium vapor, it would still would have given the greenish yellow color. Similarly, potassium chloride, if it gets F center, no matter how that F center is created, by heating in sodium vapor or whatever vapor, it gives a lilac color. It is slightly purplish color. Okay. And how can I detect an F center? We have been talking so much about color, right? So we can detect it by UV visible spectroscopy. And because ultimately we are talking about unpaired electron, we can investigate them by ESR also, electron spin resonance. Okay. And sometimes what happens is F centers are not the only color center that you can produce. Sometimes what happens is two electrons occupy the same anionic vacancies. Of course, these are non-equilibrium defect, because otherwise, if you ask me, or if you can also understand, two electrons occupying the same space is definitely not very stable. But it happens, and these are non-equilibrium defects, and when they happen, two electrons occupying one anion vacancy is called F prime defect. Okay. Now, what happens is sometime when you irradiate your material by radiation, it could be X-rays, it could be gamma rays, or it could be another high energy radiation. Chlorine ion, it gets ionized to produce chlorine atom and an electron. Okay, these electrons drift away in the material and occupy an ionic site. This particular chlorine atom forms covalent bond with the chloride ion present in the NaCl or KCl lattice. And when this chloride molecule ion is what I will call it, chlorine plus chlorine minus forming chloride molecular ion. This chloride molecular ion occupies two lattice sites. Okay, then in that case it is called an H center. So when the chloride molecular ion occupies two lattice sites, it is called H center. But when this chloride molecular ion occupies only one lattice site, then it is called a V center. Okay, so why for you it is essential to know this? It is not very necessary for you to remember what is H or V or what is FA or what is F prime or F, but just that if at all later in literature you come across these terms, then you would know where they are actually referring to. That is the whole point of this course, to make you acquainted with different terms that you might be introduced to in your future. Okay. Now, this was, I'll take a minute's break. We can go to the chat box and see if there is anything that you want to ask, but I'm sure there won't be much, because this was all the basic stuff that we talked about till now. Okay, so whatever defect we just talked about till now, whether it was vacancy or interstitial or Schottky and Frenkel, are also called zero diamond or color centers. They're also called zero-dimensional defect. And they're also called point defects. What do I mean by that? That whenever they occur in a material, they occupy only one lattice side. All right. So that is called zero dimension. They do not have any dimension or point defects. Of course, now that with the advent of very high end instruments that we have with us, I mean, which have been developed, it has actually been known that simple point defects they never occur. Why? Because energetically, if you have a interstitial and a vacancy or a group of interstitial line close by, it is energetically more favorable for them to come together and cluster, and as a result normally the point defects do not are not as simple as they appear. Okay, it is like human beings, we are also not as simple as we appear. So yeah, but still, going for the definition sake, point defects or zero dimensional defects are the defects which occupy only single lattice side. Similarly, as the name suggests, one-dimensional defect is a linear arrangement of point defect or the defects that extend in one direction. They're called line defect, and they're primarily two kinds of line defect given by edge dislocation and screw dislocation. And what are they? We'll talk about that a little later. Two-dimensional defect. When your defect extends along a plane, a 2D surface, we call them 2D defects or surface defect. And what are they? The grain boundary, twist boundary, tilt boundary, stacking fault, phase boundary, something also known as swing boundary, and we will talk about. ये दूसरा. Okay, sorry about that. Then we also have three-dimensional defects, which are also called volume defect, and we'll study about that a little only on them because they are most of the time not the inherent part of your crystal structure. Okay, so dislocation or line defect. We studied about the point defect. Now dislocation or line defect. Okay, a very, very important difference between your 0D and 1D defect, or for that matter, 0D and 2D defect. 0D defect, other than color centers, are thermodynamically formed defect. They make the crystal stable energetically. But your 1D defect or your 2D defect, they actually raises the energy of the system. They are not formed thermodynamically. They are actually formed when your material undergoes some kind of shock. For example, formed during solidification, when you're solidifying a material from your melt, or when you deform your material by applying pressure, by applying stress, or whatever, then you get the line defects. Okay, but these line defects also, like your point defects, they affect the mechanical, electronic, and photonic properties. And once they form, they occur in high densities. Okay, very, very important. As I mentioned, they are not thermodynamically generated. They have high enthalpy associated with them, and here the increase of enthalpy is much larger as compared to entropy change, and hence delta G is positive. Okay. So as I just mentioned, there are two types of dislocation: edge dislocation and screw dislocation. Now this, whenever I teach, I always ask the people whom I'm teaching to concentrate a little, because it is not very difficult to understand if you're with me, but of course not as easy to visualize as point effects also. Okay. So when do we call? By definition, what is an edge dislocation? Okay, we'll not talk of definition first. Let me first show you what is an edge dislocation. You see this particular figure. A perfect crystal, it has no deformation or dislocation. But if somehow I transform it into such a way that one particular plane of atom is actually start. See, if you try to observe this particular crystal, how does it look? A plane starts from the top, goes till the end. A plane starts from the top, goes till the end. And hence we can talk about all the rows of plane lined here. But when you come to this particular cube, what do you see? The plane starts from the top, comes to the end. The plane starts from the top, comes to the end. But here comes a point when this particular plane actually starts from the top, but it parts midways. It stops midways. Okay. This is where we have the dislocation that is called edge dislocation. Now, where does that edge dislocation lie? If you look at this point, if you look at this point, the line that would be going, I mean, the plane started from the top and parted midways, then this particular line, which was incomplete, which was not continuing, this one dimensional line is called edge dislocation. So if I look at this cube and if I put my pointer over here, then the line that is perpendicular to the plane of the screen and going inside along this unfinished plane is called edge dislocation. I hope it is clear. Let us try to visualize it in this figure. Okay. Now in this cube only, if I try to see only the front face, this is the arrangement of atoms, how it will look like. All the atoms are very nicely arranged. But when I come to this particular situation, what happens is this particular line of atoms started from the top, but here, then it was not able to extend further. So you get some sort of space here, and the line which is perpendicular to this plane of atom going into the plane of atom along this unfinished plane is the edge dislocation. And as you can clearly see that below this particular line, okay, below this particular region, the atoms are close together, they're compressed. And above this, they would be in the state of expansion, a little expansion and a little compression. And as we know from our potential energy versus R diagram, okay, see how we are referring to this. Science is always interdisciplinary. You cannot really study solid state in isolation. We have something like this, and this is your R equilibrium. Okay, तो इसके थोड़ा भी इधर या थोड़ा भी इधर आप जाओगे तो potential energy increases. And this is what we were just discussing a few minutes back, that line defects are not thermodynamically generated. They are actually associated with higher energy. They are not thermodynamically stable. Okay. So going back to what we were discussing, if you try to visualize it in another way, this was just a suppose like how do they actually look like? Suppose this crystal is there, this cubic crystal is there, and then you try to imagine it. Suppose you have this particular crystal, you have cut it this way, that is along the plane A, B, C, D. Not cut it, just try to imagine that I have an upper part and then I have a lower part. And then I also cut it this way, like along this particular line. Again, not cut it, just try to imagine. So what now I will have is, I will have four cuboids or four rectangles, two on the top, two on the bottom. Okay. Now you put your hand on the cuboid, which is on the right hand side on the top, and try to push it. Paying attention to the fact, taking care of the fact that you don't go beyond this line. Okay, even if you are trying to push it from the top, but आप ये आधे से आगे नहीं जा रहे हो, तो उस केस पे क्या होगा? Now since you have tried to push it from the right hand side, your first plane of atoms will actually bind with the second plane of atom in the cuboid, in the rectangle which is lying at the bottom. The second would bind with the third would bind with the fourth, and so on. But the plane corresponding to this particular line, जिसके आगे हम लोगों ने प्रेशर नहीं लगने दिया, उसके corresponding नीचे अभी कोई भी एटम की लाइन नहीं है. And that particular plane is actually hanging. And that particular line, which has not got a partner in the bottom plane, is edge dislocation. I hope it is clear now. Okay, I've explained it to you by three ways. Edge dislocation can be represented by either this or this. This is called positive edge dislocation, and this is called negative edge dislocation. What does it represent? This represents that your plane in the crystal started from the top and then it parted midways. This represents that your plane of the crystal started from the bottom and then it parted midways. All right. I hope this is clear. Then how do I quantify this edge dislocation? कितना मेरा dislocate, कितना deformation हुआ है? What is the quantifying term that I give to it? Okay. That is defined by something called Berger's vector and it is denoted by B. Now, how do I define the Berger's vector? Coming back to again this particular figure that we just talked about. Look at this. Suppose, now this is the plane of atom, very nicely arranged in 3 dimensions. Okay, your attention to the left hand side figure. Suppose you mark a point P. You start walking from the point P and you cover 1, 2, 3 and 4 interatomic distance. You reach here this point. Now you start from this particular point and reach 1, 2, 3, 4 and 5 interatomic distances and you reach this point. Then you again come back 1, 2, 3, 4, you're here. You again go to the left 1, 2, 3, 4, 5, you're here. So you started from P and you're back at P. Okay. Now you come to this particular thing. Now this fellow has got an edge dislocation. You start from P, move 4 interatomic distance, you're here. Move 5, you're here. Move again 4, you're here. Move 5, you will come at point Q and not point P. Okay. So to reach the point P, you will have to go back by a particular distance. And that particular distance is called Berger's vector. Or in the more polished language, extra distance that is needed to be traveled to reach the original point gives you the measure of the Berger's vector. Now, what is the and the circuit that we cover to reach at the Berger's vector at that particular the starting point, that is called Berger's circuit. Okay, and now we have talked. It's a vector. We have talked about the magnitude, but we also have to talk about the direction. डायरेक्शन क्या रहता है आपका एज डिसलोकेशन का डायरेक्शन क्या था इट वाज एट दिस पॉइंट इट वाज गोइंग इनटू द प्लेन ऑफ द स्क्रीन और द प्लेन ऑफ द पेपर okay so I can hold it vertical on my screen right now but your Berger's vector is in this direction. So the Berger's vector in case of edge dislocation is perpendicular to the dislocation line. I'll repeat. Berger's vector is perpendicular to the edge dislocation line. Okay, I hope this is clear. Take 10 seconds to grasp whatever I said, and I'll take you to the new, the second line dislocation, which is also known as screw dislocation. Whatever I just explained, was it clear to you? Tell me yes or no. YouTube पे देखेंगे कुछ है क्या दोबारा से all right. A little thing that I would also want to tell you here. The particular plane where all this action is happening, that is A, B, C, D, that is called the slip plane. And This portion A, B, F, E, this is called the slip part of the plane and this is the unslipped part of the plane. Alright. Now screw dislocation. In case of screw dislocation, we will again look at our cube, whatever we were looking in case of edge dislocation. Again, look at this normal cube. Try to cut it in horizontal half, that is upper part and lower part. And now this way, like along this particular line, you try to cut it here. Cut it means you try to imagine that these things are now mobile. Now you place your hand on the top 1/4 of the on the top rectangle, the top cuboid that you have obtained towards you. Okay, and then now try to displace it. And now no, don't hinder its motion anywhere. Earlier I asked you to stop midway. Now you just keep on pushing it. Okay, so you will have some situation like this, but only the top cuboid which is closer to you. So basically you have 4 cuboid, 2 on the top, okay, and 2 at the bottom. Now the top one that is closer to you, you're pushing it. The top one which is away from you, you're not moving that. You have to imagine the motions in this particular sense. So what happens is, if you are in the perfect cube, what you do is you start from this point and you go to this point and then you go to this followed by this. You ultimately finish the Berger circuit and you reach the original point A. But here in this case, what happens is you start from this point, okay, let's say, but now to finish the Berger circuit, you have to move this particular extra distance. Okay, you can actually imagine it like a step, this particular thing B. Okay, and in this case, this B, the extra distance that you have to travel to reach to the original point or to complete the Berger's circuit is called the Berger's vector. Here, this particular line, this line, okay, along which all this deformation has happened is called screw dislocation. And now, as you can clearly see, that this is the direction of screw dislocation and this is your Berger's vector. Now your Berger's vector is parallel to screw dislocation. Okay. I mean, it is parallel in the same direction, but it could be parallel or it could be anti-parallel to the, given the fact whether you have moved it in this direction or you have moved it in this direction. All right. So this is what screw dislocation is. Why has it got the name screw? That is an interesting thing. Because if you try to imagine the bond distances along this line EF that is being shown here, that is along screw dislocation. Now the bonds actually look like the screw, like when you move a screw inside, it actually takes that path. Because this particular dislocation has created this arrangement of atomic bonds, so it is called a screw dislocation. It is like you take that, I don't know, a screwdriver and try to move it. The way it moves, this is how your screw dislocation moves. Let me see if I can actually try to visualize that or not. You look at this particular figure, okay? And you imagine 1, 2, 3, and 4 is actually the square of atom that is on the right hand side face of the cube. Okay, similarly 5, 6, 7, 8 is the next square of atom which probably would lie inside the cube adjacent to this first face of the cube. But when you have tried to slip this particular cuboid in from right to left, what happens is 1 is still joined to 2 and this is your edge dislocation, screw dislocation, sorry. 1 is still joined to 2, 2 is joined to 3 and 3 is joined to 4. This is how it was. But now 4, rather than being joined to 1, which it was in earlier case, it is now joined to 5. 5 to 6, 6 to 7, 7 to 8, but 8 is not joined to 5, it is rather joined to 9. 9 to 10, 10 to 11, 11 to 12, 12 is not forming the square with 9, but it is joining the 13. So you can imagine that if your screw dislocation is going like this, it is actually, the bonds are going round and round about this. It is like the spiral staircase that we used to see in old Bollywood movies. Okay, that is why this particular dislocation is called screw dislocation. Difference of the Burgess vector between screw and edge dislocation is, in edge dislocation, the Burgess vector is perpendicular to the dislocation line. In screw dislocation, the Burgess vector is parallel to dislocation line. Screw dislocation can be replaced either in this way or in, uh, I'm sorry, this way. Depending on the fact whether the screw is moved in a clockwise or an anti-clockwise direction. Okay. Now, how can the dislocations are very mobile? In fact, they actually deform the crystal or better its property only by the fact that they can move. And you can annihilate them by increasing temperature or by applying stress. And how would they get annihilated? This is a very simple pictorial representation of this. Now, suppose this was, look at the first figure. Okay, suppose this was your edge dislocation, the half plane of atom. Now, as you apply the pressure from left hand side to the right hand side, what will happen is this particular atom or this particular unfinished line, which does not have any partner, it will join to these atoms. Okay, and then now this would be half. Again, you are applying the pressure, this will join to this and this would be half. So you will get this situation. Okay, and you keep on doing that. Ultimately, what happens is it will keep on, the dislocation line will keep on moving towards the right hand side, and ultimately, in the end, it will reach the top face of the crystal. And once it has reached the crystal, it will appear like a step, and then it won't be anymore a dislocation. All right, and the material will become energetically more stable. So when you apply stress, you can remove dislocations. When you apply temperature, temperature करने से कैसे होगा? Because when you increase the temperature, the atomic vibrations increases. The atomic vibration increase, then the possibility of this particular phenomena forming bonds with the neighboring atom, so that it increases, it gets better three-dimensional periodicity, that increases, and the defects ultimately move to the surface of the crystal. Okay, and very interesting thing is that this dislocations, they can not only, and they can actually annihilate among themselves also. How? For example, I told you what is an edge dislocation. It is ultimately a half hanging plane of atom. Suppose you had two edge dislocation lying nearby. One was starting from the top and parting midways, and the other was starting from the bottom and parting midways. Now, if they move towards each other in the way I just described by applying stress, ultimately one point will come when this top half and the bottom half, they will meet. Okay. So the positive edge dislocation and the negative edge dislocation, they will reach closer to each other, and we will get a undefective plane of atom with no more dislocation left in it. Similarly, okay, we can just leave that here. And this is just one example of how the actually dislocations move. It is also like, suppose you have those heavy carpets in your home, right? It is very difficult to pick them up and move. But what we do is we apply pressure from one side, it forms some kind of a hump. Okay, and then we apply further more pressure, and then that hump moves. It is similar to how a caterpillar moves. This is your let's say this is your defective, this thing, whichever direction you want to go. This is your completely perfect crystal. Then it moved this way and you had a half plane. And then it further moved and the half plane moved further. And ultimately the half plane reached here. This is how a caterpillar moves basically. Okay. Now we finish our 1D defects here. Coming to the, so 1D defect, I'll quickly summarize. We have two kinds of 1D defect: edge dislocation, screw dislocation. Edge is formed when there is a plane of atom that is parting midway. Screw dislocation is formed when the deformation happens in such a way that the atomic arrangement around the deformation is in the shape of a helical helix. Okay. Then the Burgess vector in case of edge dislocation is perpendicular The Burgess vector in case of screw dislocation is parallel or anti-parallel. Okay, and we can remove dislocations by applying temperature or by applying pressure. All right. Coming to two-dimensional defect, or these are also called surface defect. These are also called interfacial defect. So interfacial defect is a 2D imperfection, and the region that it affects is about few atomic diameters, both in thickness as well, not in thickness, in XY direction or YZ, basically around a 2D plane. Okay. Again, like 1D deformations, 1D defect, they are not thermodynamically stable. Okay. But they are metastable in nature because they are associated with high energy. All right. The first foremost example of 2D 2D defects are external surfaces. Surface of the material always, has got unfulfilled bonds. Whatever three-dimensional bonds were being formed from inside the crystal, as it reaches the surface, those bonds are not fulfilled. So it is associated with the higher energy. So external surface itself is an example of 2D defects. Then we have certain other 2D defects which we'll talk about. This is the free surface. Grain boundary. Okay. Now, how a grain boundary is formed? Suppose I have a melt and I'm trying to grow crystal out of it. What will happen? Small, chotu nuclei will start crystallizing at different places, and these nuclei will attract atoms from the melt towards itself. Okay, and then they will start growing in size. Okay, so let's say suppose these two nuclei are growing side by side. Atoms are going here, atoms are going here, and they will keep on growing. A particular point will come when what will happen is an atom that would be here, they would experience equal force from different nuclei, from these two nuclei. So they will not be able to go there, they will not be able to go there. They will just stay in there. And it will not have the structure of any of these two crystallites. And it will not have a three-dimensional structure as well. Okay. And those regions which are formed between two neighboring crystallites, they are called nothing but grain boundaries. And grain boundaries have the dimension of only few atomic diameter. Why? Because the atomic forces that are being applied on the incoming atom from these two crystallites can only exert up to few atomic diameters, right? So this is how the grain boundaries are formed. The grain boundaries, because they do not have the structure of the crystal that we are talking about, they are called defects. And because they extend in the two dimension, they are called 2D defects. Okay. So basically grain boundaries, it separate grains or crystallites with same structure and composition. Now these grain A and grain B will be two similar compounds, similar structure, similar composition also, because they are being formed from the same melt, but they will have different orientation. Okay. Again, a pictorial representation. Again, this is an SEM of how it looks. Grain boundaries. Okay. Now, grain boundaries could be low angle grain boundary, high angle grain boundary. And what defines that? You look at these two crystals, this and this. Okay. Now, this particular line shows the orientation of this crystal. And this particular line shows the orientation of this crystal. Okay. Yay. Of this crystal. This was this. Then angle between these two decides. Since this angle, similarly, angle between this crystallite and this crystallite is given by this angle. Now this angle is smaller than this one. So this grain boundary is called the low angle grain boundary. Okay. So and this grain boundary is called a high angle grain boundary. So basically what are these? They basically define the extent of misorientation between two grains. How differently the two grains are oriented with respect to each other. All right. So grain boundary, it is a region between the crystal. It actually shows the transition from one region to that of other. That is the reason it is disordered. Okay, slightly disordered. And we just talked about low angle and high angle grain boundary. This is a typical, very high resolution figure of a low angle grain boundary in cubic zirconia, which is seen by TEM. As you can see here, if you concentrate here and here, these are actually grain boundary and two grains are separate. They are in different orientation. Okay. Let's not do tilt and twist grain boundaries. Now, grain boundaries, how can we anneal them? When we talk of defect, we should also be able to see how can we, remove them. So you increase the temperature of the material. When you increase the temperature of the material, smaller grains, they will combine to form the larger grain. We heat nanopowder, what happens is it becomes bulk, it becomes micron size. What is happening? Amount of the material is same. Grains are coalescing to form bigger grains. So the number of the grain boundaries are actually decreasing. Okay. Interface boundary. This is very easy. In this particular slide, we saw that grain A and grain B had same composition. So this particular boundary between them was called grain boundary. Now, when you're talking of a solid state reaction where you've got two phases or you're doing some process where you've got two phases, then the boundary that would be separating the grains of two different composition is called an interface boundary. Okay? So the interface that separates the grain of different chemical composition or same composition but different structures. Now, how is that possible? Same composition and different structure? It will happen in the material which will show phase transition or different crystalline phases for one particular composition. Okay. Twin boundaries. Now, this is a very, very interesting defect. What happens is twin boundary is a defect across which your structure is a mirror image of itself. Okay. It is only a region that gets deformed. And twin boundaries occur in pair. So deformation brought about by this particular plane is actually undone by this particular plane. What deformation happened? Earlier this was running in the straight line. Now what happens is this atom has come here, this has come here, this has come here. And then beyond this it extends in the similar fashion. But now this particular region is the mirror image of this particular region. So twin boundary is the 2D defect across which the structure is the mirror image and they occur in pairs. So the damage done by, or the change, I should not say damage, change brought about by one is undone by other. Okay. Stacking fault. The stacking fault happens due to, as the name suggests, faulty stacking of the closed packed layer. For example, you look into this. This is a perfect crystal where you have ABC or CCP type of packing. If you look at this red line, it shows that every fourth layer is a similar one. For example, this yellow atom, 1, 2, and this is fourth layer, and then this is fourth layer. So it has a similar point, okay? But what happens is, suppose ABC, AB, and rather than C, you again have an A layer. How can it happen? It can happen by when you're growing crystals from melt or, some deformation, some temperature changes, some external shock. Now one layer is missing. So what happens is basically in this particular region, this was a cubic close packing. This was a crystal which had cubic close packing. But because of this deformation, in this region, in the entire sea of cubic close packing, you have a hexagonal close pack layer, right? And this is called stacking fault. The fault or the defect that occurs to wrong stacking of the layer is called stacking fault. Now, if you see at that red line, it has yellow, but now rather than yellow, you have a green. Okay. And the bulk or the volume defect, they are three-dimensional defects. And these defects are generally not, they occur majorly during the processing and fabrication operation. And they are like pores in your material, cracks in your material, foreign particles, impurities. All of them will actually be present inside your material. And because they occupy a certain volume, they are called volume defect or 3D defect. Because of them also, the properties are altered. Okay. For example, in some cases we form composites. We add some foreign particle. What they will do is they will harden the material. Okay. There are places there application where you need more hardened material, and this is these particles are added. They provide hindrance to the movement of dislocations. The dislocation that are already present, the 2D defect, these particles will go and sit there and they will provide movement to the hindrance to the movement of dislocation. Okay, and that provides more strength to the material. As you can visualize, if you have dislocation, your material can easily slide over it, which is what you want to avoid. So this particle goes and sits there. It hinders the movement and thus increases the strength of the material. Okay, these are some sort of volume, some examples of bulk or volume defect. Voids, sometimes you have bubbles like vacancies, cracks, pits, grooves, inclusions, precipitate, all these are the example of three-dimensional defect. Okay, so and then how do we study various kind of defect? We can study point defects by conductivity. Now this is one detailed, this thing probably will be able to cover it. But you can measure because they are ultimately vacancies or interstitial. They will aid in the conductivity. So that means if there is a change in the conductivity of the material, you will know that you have point defects. UV visible spectroscopy, we talked about the color centers. Dielectric studies. How dielectric study? What is a dielectric constant? It occurs due to polarization in the material. You apply electric field, your positive and ion and negative ion, even if they are not mobile, they will slightly shift. The negative ion will go towards the positive ion, the positive ion will go towards the negative ion. Okay. Now suppose you have a defect. The negative ion is not present at all. Okay. This will now not just one case, there will be many such cases. So this will affect the dielectric constant depended upon the separation of these ions. Now one of them is not present. So it is very easy to understand that this will lead to changes in the dielectric property, and that we can study by doing dielectric studies. Dilatometric. What is dilatometry? You measure expansion, thermal expansion. Dilatometry studies can also tell you about the point defects. Then positron annihilation spectroscopy. This is one of the sophisticated techniques. Now 1D and 2D defect. They are all of they have bigger dimensions, so they are easier to observe. And once something is easier to observe, you will simply use camera, right? So in case of this material, we use electron microscopy. In my camera, my probe is light. In electron microscopy, my probe is electron. Okay. I can also use optical microscopy, especially for the defects like twin boundaries, because our twin boundaries are the 2D defect. But yeah, they can be observed because they're slightly bigger on the surface. Color centered, of course, we covered them in the point defect, but you can study them by UV visible, X-ray spectroscopy as well as ESR, because ultimately they are unpaired electrons in it. Okay, this will discuss about how conductivity can tell you about the point effects. But I think I would rather leave here because probably I would like to know from you if there is anything you didn't understand. Otherwise, we would wind up this lecture. So what we can say is point, line and surface defect, they do exist in solid. Their number and type can be controlled by temperature. If I decrease my temperature, my point defects can reduce. Some of them would be there, but according to the formula that we derive, now the number of the concentration of defect would decrease. Okay. Defects definitely, most definitely affect the property of the material. Okay. They may be desirable or they may be undesirable. They are undesirable when you don't want that property. They are desirable, suppose I want to have a color from my material, and my point defects will go and form electron levels between my valence and conduction band. So they are providing me a path which actually lies in the visible region. I might be able to see the color. So they can be desirable or undesirable depending on what you want from that, right? Okay, it is all about us. If a property is good to us, we are happy about it. If a property is not good to us, it is undesirable. We are not happy with it. So, just to summarize, what did we do today? We studied why are materials defective at all. Then we also studied about various type of defects and how can they be classified. Then we studied about how can we classify the defects on basis of dimensions, and we studied a little more details about color centers and how can we study the defects. Okay. Beyond that, if you have any questions, anything, please write to me, or if you want, I think we have 5 minutes. We can still discuss about that. How many do we have on YouTube, Anura? 10. So is there any doubt, any question? Single crystal will not have grain boundary, Debarati. That is why it is single crystal. Grain boundary is something that separates out two crystallites. Okay. Characterization technique for dislocation. Your microscopic techniques. SEM, TEM, electron microscopy, or even when you have your dislocation can be actually, what we have is, suppose we have a crystal and it has dislocation. The crystal is first etched with some kind of acid so that it can clean the surface and remove all the debris from it or other things. And then those dislocation becomes a little more visible. And then we the electron microscope. Okay, well, guess there's no more doubts. So maybe next class, I would be a little more particular with your assignments. Probably by next class or next to next, which would be my last, I would send 2 to 3 assignments, and then we'll probably try to gauge how much of this I've been able to communicate to you. Okay. So you have a good day and good evening. We'll meet on Friday, and then Monday would be the last class of this particular module. Okay. Thank you so just. How can artifact or dislocation be differentiated? May I know your name, please? Because okay, people who do electron microscopy, they are actually very well versed with these kind of things, whether particular things. And as I said, in case of screw dislocation, you will see a different kind of patterns also. Okay. So they electron microscopists are well versed with different kind of artifacts that they can see. So they are expert in observing the thing, and there are certain patterns associated with dislocation. So they are able to identify that. All right then, we shall wind up here, and I'll see you on Friday. Thank you so much.